So great things. Two major scientific theories. Here we're going to look at this Bohr model and the quantum mechanical model. And you've already seen the Bohr model in lab with our atomic emission lines. You've been exposed to the Bohr model. The quantum mechanical model proposes explanations for the inertness of helium and the reactivity of hydrogen and periodic law. These models explain how electrons exist in atoms and how those electrons affect the chemical and physical properties of the element. So it's really all about electrons. So here's three famous people. You probably maybe recognize one of them, Albert Einstein. I like the one with the longer hair and the big, when he sticks out his tongue. This is Niels Bohr, and this is Schrödinger. And they all played a role in the development of quantum mechanics. And most people are kind of wonder about light behaving as a wave and a particle. And we can make particles behave as waves. And my proof to convince you of that, you've all looked through maybe a microscope, especially if you spend any time over there, look through a microscope. And that use visible light, which you imagine being a wave or rays of visible light. Have any of you ever heard of an electron microscope? They can also image things with neutrons. Down in New Mexico, where they have the particle accelerator, they can make a neutron microscope and image very small things, turning a particle into a wave. So there's this duality of light. It can behave as a particle and a wave. And we can do the same thing with electron. And obviously an electron microscope shows us we can use a particle as a wave. So if you heat anything up, it tends to give off light, it glows. And so this interaction of light with atoms helped shape our model of the atom. So light is a form of electromagnetic radiation. What does that mean? Well, in physics, you might be taught that light has a electric wave and a magnetic wave perpendicular to each other. We don't really need to worry about that. Light is a type of energy that travels through space at a constant speed of 3 times 10 to the 8th meters per second, or here in miles, 186,000 miles per second. That seems pretty fast. It seems like instantaneously until you try and travel to the sun or a star, and it takes a few minutes to get to our sun. Light has properties of both waves and particles. So a good analogy for a wave is when you throw a stone into a pond and that wavefront ripples out. Maybe another good example of a wave, if you tie a rope to sometimes you see people doing this at the gym with those big ropes, and you see standing waves. And of course, in physics class, sometimes you have a weight and a string and a little vibrator, and you get these standing waves, and you change the weight and do all kinds of neat things. Possibly when I was a kid, you'd take a soup can, drill a hole in it, put a long piece of string in it, take another soup can, put the string through there, and you pull it tight, and you talk to your friend, and it has that tinny vibration sound. Of course, nowadays with a cell phone, somebody's gonna be, why would you do such a dumb thing? But of course, the sound travels through the string as a wave, vibrates the end of the can, and you hear that. So yeah, sound waves we're fairly familiar with, but we can think of electromagnetic radiation behaving kind of the same. Of course, with air, a wave in air, you have regions of high pressure and low pressure. Electromagnetic radiation, you're going to have regions of a high electric field and a high magnetic field. Here we're probably only looking at one. So wavelength of light, we like to use this Greek lambda, and it's the distance between adjacent waves crest, or one cycle, however you want to look at it. So here it dips down, comes back, and here it's going to start the next cycle. So you can measure from peak to peak or trough to trough, and you'll get the same wavelength. And we imagine this wave traveling, and hence the waves on a pond analogy. And so if you're sitting here and you count how many peaks travel past you in a second, that would be the frequency. And we're going to get to frequency here in a little bit. So white light, as produced by the sun, contains a spectrum. And you all gave me that nice rainbow spectrum in that lab. And we see the colors red, orange, yellow, green, blue, indigo, and violet in a rainbow as that white light gets spread into its components. Red light wavelength of 750 nanometers, longest wavelength. I think I can't see any of these. A lot of you had trouble with the krypton because it just had that very faint violet, and that was probably at 420, 450. The presence of color in white light is responsible for the colors we see in our everyday vision. So I think the first person that did this was Isaac Newton, and I'm told there was the plague going on, so he didn't go anywhere, but he took some sunlight coming through a window. Maybe he darkened some of it off to get it in a nice beam, put it through a prism, saw that it was separated into its components. Now, what I think is amazing and neat is some guy took a thermometer and he stuck it in here and he saw that this light would heat up the thermometer more than the others. That was kind of an insightful thing to do. A red shirt appears red because it reflects red light. The shirt absorbs all the other colors of the light except the red light. So if you're absorbing a lot of this, you're gonna get the red. Turns out it's complementary colors. Whatever colors are complementary to the red, the shirt is absorbing. And our eyes see only the reflected light. All right, frequency, pronounced nu. Greek letter there is defined as the number of cycles or crests that pass through a stationary point in 1 second. Wavelength and frequency are inversely related. The shorter the wavelength, the higher the frequency. And I can't help myself because we do this in general chemistry. This isn't general chemistry, but c is the speed of light. And if I divide that by wavelength, I'm going to get frequency. So it makes sense if I times frequency times wavelength, I should get the speed of light. So the main point of this, it says wavelength and frequency are inversely proportional. So as the wavelength gets smaller, what happens to frequency? It increases. And then of course I could probably rearrange this, and if wavelength gets longer, frequency gets lower. That is the inverse part of this. So here's an interesting photograph from Life magazine way back when. And you might have noticed this at home. I always notice that at home, and you take your pillow and you go, what do you see? You're like, man, I need to dust. I thought, so the light is being scattered off small dust particles and you see nice beams of light. And sometimes you see this with weather phenomena, nice beams coming down. Light can be viewed as a stream of particles. A particle of light is called a photon. We can think of a photon as a single packet of light energy. The amount of energy carried in that packet depends on the wavelength of the light. The shorter the wavelength, the greater the energy. Light carries more energy if their crests are closer together. That means higher frequency, shorter wavelength. Violet light, shorter wavelength carries more energy per photon than does red light. All right, so what do we know thus far? Electromagnetic radiation is a form of energy that travels through space at 3 times 10 to the 8th meters per second. It behaves like a wave. That means waves can be added, subtracted, it diffracts, or particle-like properties. Einstein used the particle property to explain the photoelectric effect, where a photon of light can kick electrons off a piece of metal. The wavelength of electromagnetic radiation determines the amount of energy carried by one of its photons. The shorter the wavelength, the greater the energy of each photon. Frequency and energy of electromagnetic radiation are inversely related to its wavelength. So it turns out only a small little band is what we see with our eyes of the whole entire electromagnetic spectrum. So here's radio waves, wavelength 10 to the 5/5 meters. That's pretty long. And notice here, by the time we get here, we're getting kind of short wave, but the visible is right in here. So is light a particle or a wave? Has properties of both. Photoelectric effect shows that a photon has momentum, that's a particle property, and diffraction is a wave property. So yeah, radio waves, microwaves, we can't see them. We can see infrared with an infrared camera. And of course, X-rays we develop with film and visible, just a small little sliver, wavelengths of 400 nanometers to 750 nanometers. So that's real short. 1 times 10 to the negative 9th is nanometers. So the shortest wavelength packs in the most energy in a photon. So gamma rays there would have the most energy. Gamma rays are produced by nuclear reactions in the sun and stars, and in nuclear reactors and particle accelerators, whatnot, we can make gamma rays on Earth. Excessive human exposure to gamma rays is dangerous because of the high energy of gamma ray photons can damage biological molecules. How many of you want to get on a spaceship and be put to sleep for 20 years so you can travel to some distant planet? No, you go out in outer space and you get exposed to a lot of gamma rays and horrible things. Fortunately, down here on the surface of the Earth, our atmosphere filters out a lot of those things. After gamma, we're going to look at X-rays with longer wavelengths and lower energy. So these are familiar from medical use. So I was getting headaches, and so I went to the doctor, and this is the X-ray he gave me. X-rays pass through many substances that block visible light and are used to image bones and organs. And maybe when you got your X-ray done, the technician had a little badge, and what they have to do is turn in that badge every now and then, and they see how much exposure the technician got exposed to, and if it's high, then they know there's a problem. It doesn't protect the technician at all. So several yearly exposures to X-rays are relatively harmless. You don't want lots of X-rays. So when X-ray machines first came out, I'm told that like at Sears and Roebuck, they had an X-ray machine right there by the shoes. And you'd put on a shoe, put your foot down there, and they had a fluorescent screen, and it was horrible. Everybody in the stores getting exposed to X-rays. But you could look at your foot, move your toes around. Between X-rays and visible light is ultraviolet or UV light, familiar to us as the component of sunlight that gives you a nice suntan, or if you're fair skinned, does what to you? Makes you look like a lobster. And of course, melanoma is what you want to avoid there. And if your living room drapes fade and your dashboard on your car cracks, that's all due to primarily ultraviolet light. Packs enough energy to break chemical bonds. All right, I'm gonna pick on one person. John, can you tell me the number here? John told me he was colorblind. So if you can't see Kinsey here, you're colorblind. Next on the visible spectrum, light, it ranges from violet of a shorter wavelength, higher energy, to red, longer wavelength, lower energy. And photons of visible light do not damage biological molecules. Photons of visible light cause molecules in our eye to rearrange, which sends a signal to our brains and results in an image being produced in our brains. Past visible is infrared. So we talked about that with our thermochemistry a little bit. When you go out and you feel that nice sun, you're primarily feeling the infrared, and all warm objects, including human bodies, emit infrared. That's why an infrared camera works. While infrared light is invisible to our eyes, infrared sensors can detect it and are often used in night vision technology to see in the dark. In the infrared region of the spectrum, warm objects such as human bodies glow as a light bulb glows in the visible region of the spectrum. And a lot of remote controls have infrared that goes out. So here's a person, that didn't show up very well. And here's an infrared camera. Warmest areas are red, the coldest are blue. After infrared, we get to microwaves. Longer than visible, but shorter than radio waves. It's coming up. Radar and microwave ovens. Microwave light has longer wavelengths, and then for lower energy per photon than visible or infrared light. And water likes to absorb infrared light, and it causes causes it to rotate. And so at the beginning, we've talked about kinetic energy, and a gas having a lot of kinetic energy, it's moving around. So when you impart this motion to water, it thermally heats things up. It heats up things around it. They are lying here. Substances that contain water, such as food, are warmed by the radiation of a microwave oven, but substances that do not contain water, such as a plate, are not. How many of you own plates that get hot? It gets hotter than the food. It's so annoying. So this is something from my era. It's called a ghetto blaster. And that's how we used to listen to music. We didn't have Spotify on our phones. And you can't carry your phone like this, can you? All right, longest wavelengths of light are radio waves, which are used to transmit signals used by AM. What's that? Amplitude modulation, and FM, frequency modulation radio. Cell phones, television, and a lot of forms of communication use radio waves. So too much radiation can give you cancer, and a little more radiation, we can kill cancer. So radiation can be a treatment to kill cancer cells. X-ray and gamma rays are sometimes called ionizing radiation because the high energy in the photons can ionize atoms and molecules. And when this ionizing radiation occurs within biological molecules, causes bonds to break, change, destroys them by cooking them down, really. Doctors can use ionizing radiation to destroy molecules within unwanted cells, such as cancer cells. So normally this thing can spin around at all these different angles. So here's a tumor, and so where these things intersect will get the most exposure. Of course, you have all this healthy tissue here, and you don't want to expose it to lot. You can see this one's coming through. All right, so we try and minimize the exposure by appropriate shielding and targeting of the tumors from multiple directions, minimizing the exposure to healthy cells, maximizing the exposure of cancerous cells. Well, enough of that depressing topic. Atomic emission is akin to elemental fingerprints. What gas is in here? You saw it in lab? That'd be neon. Of course, if you go around town, see a bunch of other colors, you'll realize that a lot of them have argon, some maybe CO2, some N2. You'll recognize this as hydrogen, mercury. So a long time ago, big powerful street lights always had that blue glow, and then pretty soon they'd all be amber because they came up with sodium vapor lamps, and nowadays they're all getting replaced with light emitting diodes. So here's a white light spectrum, looks like a rainbow, and here's the hydrogen spectrum. It's reversed from the spectroscopes in lab, and here's neon. A lot of you couldn't see the ones down here. So white light, continuous, with some radiation emitted at every wavelength. The emission spectrum of individual elements includes only certain specific wavelengths. That's why we see just lines. And here's how we split our hydrogen spectrum to see the 3 colors and 4 emission lines that we saw. So the beginning slide had Bohr, Schrodinger, and Einstein. And Bohr was the one who looked at emission lines and came up with this model to explain the results. Lowest energy, higher energy. Energy is conserved when an electron moves around in these orbits. The energy of each Bohr orbit is specified by a quantum number n, and we have these integer values. 1, 2, 3 is fixed or quantized. Electron can't be right here at 1 1/3 or 1 4/5. It can only be at 1 or at 2. And that's why we don't see the rainbow. We see specific lines. When a hydrogen atom absorbs energy, an electron is excited to a higher energy orbit. And then when it falls down, it emits a photon. So the light emitted by excited atoms consist of specific lines at specific wavelengths, and we can use these to tell what elements might be in outer space. We can also use it to identify elements here on the Earth. So we're going to move on from the Bohr model, but the Bohr model was successful that it predicted the lines of hydrogen emission spectrum. It failed to predict the emission spectrum for like neon that has a bunch of 10 electrons. For this and other reasons, the Bohr model was replaced with a more sophisticated model called the quantum mechanical or wave mechanical model. However, with the Bohr model, you get introduced to your first quantum number n. Well, if you look over here on the periodic table, the 1, 2, 3, 4, and 5, we can think about as being designating the principal quantum number.